Hello and welcome to Section 4, where we're going to discuss gravity, orbits, and the tides. For our introductory picture, we're going to look at some of the distances that some of the objects are out orbiting the sun. And my favorite is going to be Voyager 1, which is currently at 146 astronomical units away from the sun. For perspective, Pluto is about 40 AU away. So Voyager 1 is very far away now. It is the record holder for the furthest away man-made object and still communicating with us today. So with that, let's dive right into our conceptual questions. And this time, we're going to have what I call the drop ball shot ball. So in this setup, one ball is going to be just dropped. Simultaneously, this ball is going to get a horizontal kick that direction. And the question to you is, which one is going to hit the ground first? Will it be the drop ball because it travels a smaller distance? Will it be the shot ball because it's moving faster? Or will it be the same, that these motions will be independent of each other? All right, pause the video, give yourself a moment to think of an answer and why, and when you come back, we'll go ahead and do a demonstration to show this off. So here's our drop ball shot ball setup. The red ball is going to be launched towards the camera, whereas yellow is going to plummet down towards the ground. And the question is, which one will hit the ground first? Yellow because it travels a smaller distance, red because it will travel faster, or does it not matter? So let's go ahead and do the experiment and find out. What you're looking for, you want to visually watch red and yellow touch the ground, and it helps the audio cue when you hear them touch the ground. All right, here we go, firing. Well, there you have it. They will hit the ground at the exact same time. And that's just due to gravity. Everyone is having the same acceleration, that little g, 9.8 meters per second squared, down to the ground. The trajectory going this direction initially didn't matter. Both of them are going to accelerate down towards the ground at the same rate. As you just witnessed, regardless of one ball being dropped or shot, they will hit the ground at the same time. And that's because the motion this direction is independent of the motion this way. Both balls will feel an acceleration down towards the ground, and because neither one of them initially is moving up or down, they'll fall the same distance at the same rate in the vertical direction. This horizontal motion is independent of the vertical motion. So if you want to do a nice review of Section 3, specifically Newton's laws of motions, there is a excellent source. This is about a 4-minute animated video that goes on this astronauts on their mission to Mars, and it'll walk through the different times that the first law, second law, and third law of motion apply throughout their entire trip. So that's a wonderful review that I can recommend to everyone. In Section 4, we're going to build up the model of Newton's law of gravity, combine that with his 3 laws to explain consequences of, say, planetary motion and their orbits. Then in the latter half, we'll talk about the tides and the effects that tidal forces have on a solid body. Recall that Galileo showed that all things near the surface of this planet will fall with an acceleration of little g, 9.8 meters per second squared. And it doesn't matter how massive you are, how much weight you are. It could be a bowling ball, it could be a tiny little piece of tissue paper. They're all going to accelerate at this 9.8 meters per second squared towards the Earth. So a little distinction we'll make is what we say is your weight of force versus your mass and acceleration. Recall Newton's second law, F equals ma. Well, your acceleration is the g on the surface of this planet. So when you weigh yourself in pounds, you're not actually weighing your mass, it is the force. It's a weird thing, pounds is not the unit for your mass, it's a English unit for the amount of force that you produce. So, recap, mass. Think of mass as the number of things that you're composed of, whereas weight, your weight is how much of a force is pulling you down towards the planet. And so we'll talk later on about how your weight can change based on what planet you're on, what rock you're orbiting. Now for a little segue that I need to discuss, because I often see images like this on the internet. They're constantly shared with me. So let's talk about this. And the way these things are always presented, it'll be some sarcastic comment about like how funny speed is, and you'll see this example of here's Earth. And Earth is rotating at a very rapid speed. Every single one of us right now, you, me, the cars, trees outside, we're all orbiting, rotating around Earth right now at about 1,040 miles per hour. And the joke is that, well, everyone just feels perfectly calm and natural. You don't even feel this, massive speed. Significantly faster than anything you've ever ridden in. And continuing on with the hyperboles, you could be driving in a car at like 60 miles per hour and feel perfectly fine. I would bet a large sum of money that a large chunk of you have been texting while driving at these fast speeds, eating a hamburger or whatever. You feel perfectly safe at this speeds. And then the joke goes on to say, well, if you were to go down the slide or, say, roll out of bed and you're terrified, you're screaming because of how fast this is. But in terms of speed, at like your max in this example here, you're only going to go about 10 miles per hour. So this is a perfect example highlighting what I mean about speed versus acceleration. Because let's look at this now in terms of accelerations. People want to talk about how the speeds are funny, but really it's our accelerations towards the planet. Start with the center example. When you're going at 60 miles per hour, you're going at a nice, steady, constant rate, there's no acceleration. You're at a constant velocity, so you don't feel any forces. Remember, Newton's second law. When you are falling towards the Earth, there's your gravitational force. There's 1g pulling you down, and it is a large acceleration. So that's why you get this plummeting feeling. Your guts squeeze into your body. You're like, oh my gosh, I'm scared as you fall at this rate, because there's a high acceleration pulling you to the ground. As for Earth's rotation our single day, yes, we are going at a blistering fast speed, 1,040 miles per hour. But this acceleration is minuscule. Put it in comparison, this 0.03 meters per second squared compared to 9.8, our rotational acceleration is equivalent to 0.03% of our gravitational force, our acceleration down towards the surface of this planet. So there you have it. It's not speed that's the funny thing, it's our accelerations. And recall, whenever there's an acceleration, by Newton's second law, there must be a force. Brief reminder about our units and our terminology here. When I say mass, our SI unit, our Scientific Standard International Unit, is going to be the kilogram. Acceleration, meters per second squared. Force, coming from second law, F equals ma. Our forces are measured in newtons, named after the person who first quantified them. And based off the second law, you can see that a newton is just kilogram meter per second squared, a mass times acceleration units. And the last comment, weight. Your weight in pounds is a force. Your weight is just another example of newtons, following how much you're going to, say, body slam someone or pull the elevator down.